Atomic structure agnostic analogy. That's a mouthful for a tall person. Any case, this is the first part of our atomic structure unit. We're going to look over the models, the early models of the atom, to get a firm understanding of all the components of an atom and all the theories that result from them. In any case, we started with the Greek philosophers, okay, Democritus, okay, and I think I misspelled this. This is Democritus, but in any case, he was alive between 460 and I believe 370 BC. And Democritus was the first to come up with the word atomos. And atomos, it means indivisible particle. And his idea was that if you were to slice matter into smaller pieces, okay, so to cut matter in smaller pieces, you would eventually come up with units of matter that all things are made up of. And that is what he called his atomos, or his indivisible particle. And this is called the indivisible theory. Because once you slice matter into smaller and smaller pieces, you eventually come up with atoms. And these are indivisible because all matter is made up of these types of atoms. Okay, Aristotle came a little later, not that much later. I believe he is 384 BC, so just a little bit later, to 322. Kind of weird. Back then, time was going backwards. Not actually, it's just that from before Christ we started counting that way. But Aristotle believed in the indivisible theory. Indivisible theory. And in this theory, if you were to cut matter in half, you would eventually have just smaller and smaller pieces of matter. So the idea in the indivisible theory, which went against Democritus, is if you have matter and you slice in half infinitely, you would get just smaller pieces of matter. And that was the indivisible theory. Now, Aristotle was held in much higher regards than Democritus. So, of course, this theory, this way of thinking that matter is just made up of what it is, and if you were to slice it into smaller pieces, you just get smaller pieces of it, okay, lasted over 2,000 years. So that type of thinking lasted for 2,000 years. It wasn't until John Dalton, okay, revisited atomos with the modern atomic theory, okay, and he had about 5 of them, and I want you to list all 5 of these, and I'm not going to write them for you, but I'm going to show you where to look for these 5 postulates. But understand, John Dalton started the process of the modern atomic theory really because of the law of definite proportions. He took a lot of people's works, Joseph Priestley, Prost, Lavoisier, a bunch of those early chemists who determined conservation of matter, and all kinds of early works by the chemists, the grandfathers of chemistry, if you want to say. And from their works and some of his interests, which included weather, because he was really a school teacher, an English teacher, he was able to build this modern atomic theory. I would say the biggest piece of evidence was the law of multiple proportions that we already talked about. And this is the law that showed that if you had two different elements, let's say nitrogen and oxygen, okay, that you would make a whole bunch of different types of compounds. You can make NO, NO2, okay, N2O5, okay, but if you look at these two, if you have two compounds that make multiple different type of compounds, the mass ratios between these two compounds would always exist in whole number ratios. So if you made NO2, it would be twice as massive as the oxygen in NO. And these whole number differences led John Dalton to believe there was whole number pieces of matter involved, and that's where he brought back the atomos theory. So what I'd like you to do is go find those at least 5 different postulates that are listed in the presentation I have for you. I'm going to go there now. So here are the 5 main points of Dalton's atomic theory. Elements are made of tiny particles called atoms. All atoms of a given element are identical in masses. Now, we haven't learned about isotopes yet, but they're coming. The atoms of a given element are different from those of any other element. Atoms of one element can combine with other atoms of other elements to form compounds. A given compound always has the same relative number of types of atoms. And of course, 5, atoms cannot be created, divided into smaller particles, nor destroyed in the chemical process. A chemical reaction simply changes the way atoms are grouped together. Okay, of course, there are some exceptions because he didn't know about these things. So please write those down. I will pause and wait for you, so hit pause and write those down, please. Now that we're done with that, we should realize that there are these things called law of multiple portions. Okay, we went through this the other time, and if I was to just get rid of this box here, you can see that carbon and CO2 make carbon monoxide, or carbon and oxygen make carbon dioxide, and you can see the mass ratio is 3 to 4, or 3 to 8. That's the ratio of mass in his reactions, and these are whole number multiples, so there's twice the number of oxygens. Of course, they didn't have these, so the law of multiple portions was a very important, I would say, experimental find to lead Dalton that way. Now, of course, we've been through this already. Another person who came up with some important background information that supported John Dalton's atomic theory was, of course, Gay-Lussac and his work with atomic volumes. And we've been down that road before as well. And his atomic volumes, Gay-Lussac, and this is all other stuff that John Dalton did, but let's go quickly through them. Gay-Lussac, okay, was able to find whole number ratios. He didn't know about what was inside these things, but he said very clearly, if you remember, that we have whole number volumes that react with each other. He found exactly how much hydrogen gas, how much oxygen gas was needed to make exactly how much water gas. And these ratios were whole number. Even though they had a refute of what was inside, these whole number ratios led to, again, whole number amount of particles. Of course, we talked about who reconciled these differences, and of course that was Amadeo Avogadro's hypothesis. Equal volumes, equal number of particles led us to figure out what was inside. But as we transverse down this road of modern atomic atom theory, we can see that we have seen atoms already through we call scanning tunneling microscopy, and we have images that we see. World's smallest movie we talked about. Okay, and here's some actual pictures of this stem, they call it, of atoms feeling around. The old way of kind of seeing atoms, or at least getting an idea for where atoms are, was X-ray crystallography. Okay, most famous by Rosalind in her DNA. All right, this is actually an image I got from Brookhaven National Lab of actual, I believe, nanotubes growing, okay, in electron microscopy. And that's, of course, improved as well. Now, from all of this, we got to be able to convert to moles, okay, and now it leads us now to J.J. Thompson's very famous discovery. We're going to take a pause here and go back to drawing the model, okay, for John Dalton. So all these things you should have put here that I talked about, and let's draw his model. And his model, we think, was a solid sphere. Okay. Why? He had no reason not to believe it wasn't a solid sphere. That's what we think. So it's a solid sphere, not very, I don't know, creative, but that was his model of the atom. Put your hand out of a window, air moves your hand back, so clearly things are colliding with you. He did a lot of work with pressure, and pressure is due to force over an area. So why wouldn't you think, okay, with his work in pressure, that these atoms were solid spheres? So now we're moving on to the very famous J.J. Thompson, okay, 1897. He worked with a cathode ray tube, sometimes called a Cook's tube, and it certainly was something that he did not develop. He was just trying to explain the phenomenon, and he did a lot of work with that. So in his work, very importantly, he discovered a piece of the atom. And let me bring you back to my presentation. Now, a Cook's tube was a tube that was partially almost evacuated of air, just a few particles of a gas. And they shot a high voltage through the tube. By shooting a high voltage through the tube, this energy, okay, creating negatives and positive places for the tube. So what we did was, by providing a tremendous amount of voltage, which is energy for the charge to flow through, we created a negative spot and a positive spot for the tube. And what happens is, what little gas is left in here, okay, what happens is the negative part of the tube, or the particle that we call the atom now, the negative part gets ripped off and sent toward the positive. And those negatives go toward the positives are something called the cathode ray. The cathode, we're going to learn, is the negative part of the, let's say, electrolytic cell. So we'd have an anode of a battery throwing a voltage or throwing charge down here, and this is the cathode, and this is the anode of electrolytic cell. So they call it the cathode ray because the ray started from this negative end to the positive. So the cathode rays seems like it's shooting from the cathode this way. But what's really happening is the energy is the positive charge being developed here, and a voltage is a potential difference of charge. You have a lot of negatives and a lot of positives over here. By creating a large difference or differential in charge, these negatives are yanked to this incredibly high positive. And when they're yanked, okay, what you leave is the positive ions. And these positive ions actually migrate toward the this way, and sometimes they call those anode rays. But the cathode rays, they found a beam of electrons, or they found a beam of particles. And these beam of particles were directed toward this positive. And they were able to, and you should watch the demonstration in my next part of this. There's a guy that shows you what a cathode ray looks like, and here it is. And play this for me. What he's doing is beam is shooting this way. The negative, the positive part is here, and the cathode is right here, the negative. So the electrons are being ripped down this way. Now this is a phosphorescent piece of paper that gets charged. In any case, what happens here is that clearly there's some kind of beam, and this beam really perplexed people. They didn't know what to think of it. But what J.J. Thompson did was he set up an experiment where he basically took a magnetic field and kind of kept the ray from going in one direction, and then shot an electrical field above it and kind of kept it going another direction. And then by basically changing these fields, he could measure how much he could move this beam. Please look at this. This guy's moving this beam with a magnet. I have a question there. But by moving this beam, he figured out the mass to charge ratio of these particles. And by knowing the charge of the plates, he knew how these things reflected. So he knew the charge and found out these were negative charged particles. What was awesome during the time was, his statement was, could anything at first slightly seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen? What he means by that is, in his beam, he found the mass to charge ratio, that's the mass of the particle, by how much we're in there, to the charge, meaning how much charge he had to add to move it or attract to it, to be somewhere near 2,000 times lighter than a hydrogen atom. Hydrogen was the lightest atom. He found something that was 2,000 times lighter. So led him to believe that he found a piece of the atom. But he did not find a particle. He called it a corpuscle, okay? But we later found it to be the negative part of the atom because with a positive plate, we would find it bend downward, okay, as you will see in that demonstration, okay, or upward depending on the field. So he found the first person to find a piece of the atom, and he won a Nobel Prize for that. And there's some more work here that I want you can go through to see what he did here. It's pretty fascinating. But also, there's something called cathode rays. Canal rays, I'm sorry. The canal rays, as I mentioned before, were the positive parts of the cathode ray. Meaning, as we rip off the negatives, and now known to be electrons, that what's remaining is positive ions would go toward this collector. And the interesting part about J.J. Thompson's work is when he put different gases in here, he noticed that that cathode ray was always acted the same way, that mass to charge ratio. It would take a certain amount of charge to move the beam a certain way. And by the way, cathode ray tubes, CRTs, were used before the flat screen TVs. Your parents remember these heavy tubed TVs that had electrons moving around to create the color and the images on your TV before plasma and LCD. Any case, interesting enough, when these positives are pulled back to this collector, these positive ions were always different. Why were they different? They were different because atoms are made with a different number of protons that make it positive. Now, he didn't discover protons, but these canal rays gave us a hint that the atom is made of the same type of course, electron beams are always the same, but the rest of the atom differed by the number of heaviness because the charge to mass ratio was always different based on how many, or what type of, I should say, atom was left. Pull electrons off, you're left with positive ions, and these positive ions had protons, and of course later we found it to be neutrons as well that gave the mass of the atom, but they differed because, as we know, different atoms have different number of positives. So that was something very important in that finding of canal rays. Now, let's go back to my worksheet. All right, so what did he discover? Well, you can say he discovered an electron. He actually never called it an electron. He always thought he wanted to name it a corpuscle, but it never caught on. Now, he discovered the electron, a piece of the atom, but really what he found was the mass to charge ratio. How he discovered the electron was not like, oh, I see an electron. He saw that the mass to charge ratio was what? 2,000 times smaller than hydrogen. That is what gave him the clue that it was a piece of the atom. Okay, now his atom was a little different. Yes, it's somewhat solid, but his atom was different. He had these negatively charged electrons. Let me just draw them in a different color. So I draw these E negatives. Now these E negatives were electrons that were embedded in the atom, outside the atom. There was no organization. And you would say these electrons were haphazardly put on this solid, somewhat solid sphere, and there was no organization. And what's more important to understand is that these negatives, understanding that if you have a negative in an atom, there must be positive. So J.J. Thompson's model of the atom, was that this space in between, was made up of positive. So he believed there was a positive smear, so to speak, that the electrons were in. So this positive smear, if I can say that, all right, that's not the same green, but in any case, he believed that these positives were in there somehow, spread out through the entire atom. And because these electrons are haphazardly floating in this positive matrix spread out through the entire atom, they famously call this the plum pudding model. Now, why plum pudding? Because I guess I've never seen plum pudding. The plums are just haphazardly put in here. There's no organization of the electrons. Now, these are not protons. These are just positive charges that are spread out through the entire atom. Okay, so make sure you've got the most important points of what J.J. Thompson did. Yes, we say he discovered the electron, but specifically, Okay, it was this mass to charge ratio that gave him the hint. Okay, and through work of the Millikan's experiment, they actually found the charge of an atom, and a little bit of also they found Avogadro's number through that work as well. Okay, any case, so we move forward to a very famous experiment called Ernest Rutherford's gold foil experiment. Now, the gold foil experiment, it was very, very important. Okay, this is an important discovery that I'm going to let you discover through, I believe, slide 41, 40, 42, 43, and the presentation. And what I will say to you this, the model did change this way. Ernest Rutherford's model, okay, looked a lot like this, okay, where he had nucleus, okay, he had a nucleus of an atom. He knew it was positive. Okay, the electrons existed. Okay, where they weren't in the nucleus. That's all we know so far. So his model was a nuclear model. Okay, and make sure you put down the important pieces from the presentation, okay, and fill that out. Hope that gave you a good start. Now, make sure you go through that and watch the, of course, the animations I'll show. So starting on this slide here, Ernest Rutherford and his famous experiment. You want to do some reading here, and then you want to go through, and you definitely want to watch these animations. Click these flashes that'll take you to my webpage. Click on this flash. It's a very important flash right here. And lastly, you have to play this one, okay, and read about these conclusions here. So these are the ones you want to work through, okay, and fill in the rest in. Okay, have a good time.